Welcome back, focused learners, to another explainer. Today, we're tackling an absolutely massive milestone in Algebra 1, which is mastering polynomial fractions. Now, if you've ever stared at a giant block of algebra packed into a fraction and just thought, no way, how on earth do I simplify this? Well, you're in exactly the right place. So go ahead and grab your mental tool belts because we're going to learn how to multiply and divide rational expressions with total confidence.
Okay, let's dive into this. Here's our roadmap for today. 1. Definitions. 2. The addition trap. 3. Multiplication in action. 4. Division by reciprocal. And 5. Recap and transfer task.
Section 1. Definitions. Setting the foundation.
So, to manipulate these expressions safely, we first have to know exactly what they are. A rational expression is simply a quotient, or a fraction, made up of two polynomials. That's really it. It's just a fraction where the numerator and the denominator have algebraic variables in them. If you know how to work with basic fractions like 3/4 or 1/2, you already possess the fundamental logic needed for this. The only difference is that now we've got variables in the mix. But you've got to notice that crucial condition at the end there, with a non-zero denominator.
Because a rational expression is a fraction, the denominator represents division. And as we all know, dividing by zero completely breaks the laws of mathematics. It is mathematically undefined. Therefore, the denominator is essentially a danger zone. Any variable value that makes that denominator equal zero is what we call an excluded value, or a restriction. Before we do any actual math, we always have to scan the denominator and declare, hey, x cannot equal this number.
Section 2. The addition trap. A common misconception.
Now, what's really interesting here is how clearly we can see the difference between a mathematical crime and a mathematical victory. Look at the left side, the addition trap. When students see an x plus 2 on top and an x plus 3 on the bottom, their brain instantly wants to cross out those x's. You absolutely cannot do that. You can never, ever cancel terms that are joined by addition or subtraction. Instead, look at the right side for the correct method. We can only cancel common factors that are joined by multiplication. Factors multiply, terms add. If you remember that, you'll avoid 90% of the errors in this entire unit.
Section 3. Multiplication in action. The core procedure.
So, the crucial point is strictly following this four-step sequence. Step 1, factor everything completely, both numerators and denominators. Step 2, stop and identify your excluded values. Find those danger zones we talked about. Step 3, cancel only the common factors between the top and the bottom. And Step 4, multiply whatever is left over straight across. Let's actually see this in practice.
Check out our multiplication example. We've got a rational expression with a numerator of x squared plus 5x plus 6 divided by a denominator of x squared minus 4. And all of that is being multiplied by a second expression, x minus 2 divided by x plus 3. Now, your brain might be screaming to start crossing things out immediately, but hold on a second. Visualize our four steps. First up, we need to break these polynomials down into their multiplied pieces. Basically, we need to factor. Following our steps, we factor that first numerator into x plus 2 times x plus 3. The first denominator is a classic difference of squares, so it becomes x plus 2 times x minus 2. That second fraction, well, it's already simplified. Now for step 2, our excluded values. Looking at the bottom, we can immediately see that x cannot equal -2, +2, or -3 because any of those would create a 0. We have to carry those restrictions with us. Step 3, cancel common factors. The x plus 2 on top cancels the x plus 2 on the bottom. The x minus 2 cancels diagonally. The x plus 3 cancels diagonally. Literally everything cancels out, leaving us with a final, beautiful simplified product of just 1. But remember, the answer is 1, provided x does not equal those restricted values we just identified.
Time for our first interactive check. Ask yourself, in the expression x plus 4 times x minus 1, all divided by x minus 1 times x plus 7, is it mathematically legal to cancel the x minus 1 pieces? And based on what we just learned about denominators, what are the excluded values here? Just think about it for a second.
All right, here is the reasoning. Yes, you absolutely can cancel the x minus 1 pieces because they're factors. They're grouped in parentheses and joined by multiplication, so you're good to go. As for the restrictions, looking at the denominator before we canceled anything, we can see that an x of 1 or an x of -7 would make the bottom 0. So those two are our excluded values.
Section 4. Division by reciprocal. Applying fraction rules.
Let's move along and see how this builds into our division setup. We have a rational expression, x squared minus 9, divided by x plus 4, and it's being divided by another rational expression, x minus 3 divided by x squared plus 4x. Do you remember the old rule for dividing fractions? Keep the first fraction exactly the same, change the division sign to multiplication, and just flip the second fraction. We're simply multiplying by the reciprocal of that second expression.
Let's work through this one safely. First, we rewrite it as multiplication, flipping that second fraction so the x squared plus 4x is now on top. Next, we factor completely, breaking down that difference of squares and factoring out the greatest common factor of x. Now, we've got to identify all of our restrictions. We check the first denominator, which tells us x cannot equal -4. We check our new flipped denominator, which means x cannot equal 3. But wait, we also have to check the original denominator of the second fraction before it was flipped, which tells us x cannot be 0. We have to carry all three of those restrictions. Finally, we cancel the common factors, leaving us with x times the quantity x plus 3.
This brings us to our second pause check, and I really want you to think critically about this one. Why do we go through the trouble of checking the original denominator of the second fraction and the new denominator once we flip it? Like, why do both sets of restrictions apply to our final answer?
Well, the logic is perfectly rooted in our definitions. In the original problem, that expression was a denominator, right? So it couldn't be 0. When we change the operation to multiply by the reciprocal, the old numerator drops to the bottom and becomes a brand new denominator, creating a totally new danger zone that also cannot equal 0. Because both states existed during the solving process, the restrictions from both states must be carried through to the final solution.
Section 5. Recap and transfer task. Bringing it all together. Rational expressions are simply algebraic fractions that mathematically require non-zero denominators to avoid being undefined. To manipulate them safely, you must factor everything completely and cancel only common factors, strictly avoiding the trap of canceling individual terms joined by addition. When performing division, your strategy is to multiply by the reciprocal of the second expression, ensuring you track and carry all original and newly created denominator restrictions through to your final answer.
And this brilliantly illustrates how interconnected these algebra rules are, which brings us to our final transfer task. Imagine you have a rational expression, but you're dividing it by just a standard polynomial, not a fraction. How would you set that up? And more importantly, what would happen to your excluded values during the flip? Think about how a whole number can be written as a fraction over 1, and I'll leave you to ponder that puzzle. Thanks for joining me on this explainer, and keep practicing those mathematical structures.